Good day, everyone. My name is Fang from Xuzhou University of Technology. I'm really honored to have this opportunity standing here to have my presentation for my paper, and you are welcome to communicate with me by email shown on the screen. My paper is named Research on CRM Boosts PFC Converter based on gallium nitride device, and it consists of 5 parts. First of all, its introduction. In this part, I will explain the reason for what I do this research and what we can do for industrial area. In the second part, I will show you the theory analysis of CRM boosts PFC converter based on gallium nitride device, and the comparison of static characteristics between the cascode gallium nitride transistor and silicon device is shown. And in the third part, we will talk about basic principles of CRM boost PFC converter. In the fourth part, I will show you how the experimental platform was built and the results were analyzed. At last, the conclusion can be obtained with the test results. So let's start. Power factor correction, PFC as known, improves the harmonic generation equipment in rectification, which is the primary method to solve the problems of low PF. PFC converter improves PF value, makes input current and input voltage in phase, corrects the input current waveform, and reduces the distortion and harmonics. Is more and more necessary for power conversion equipment to improve efficiency and minimize module size while maintaining and improving electrical and thermal performance in consumer electronics. At the same time, following the development concept of socialism of Chinese characteristics in the new era, power products have the development goals of high efficiency and miniaturization. The volume of the PFC converter usually accounts for a large percentage of power supply equipment, which directly affects the power density of the power adapter. In response to the advocacy of gradually building energy consumption modes of saving, efficient, clean, and low carbon society, improving the efficiency and power density of PFC converter is an effective way to realize efficient and clean power products. In this paper, the output of PET based on dual PWM is analyzed. The dual-loop decoupling control strategy is adopted both at the input and output ends, and the dynamic response speed of the control system is improved by voltage feed-forward. The intermediate isolation portion is controlled with an open-loop control strategy. There is a need for power factor correction converters to improve performance and reduce device size while maintaining a high power factor in the consumer electronics arena. Increasing the switching frequencies is the essential way to increase the power density of the PFC converters. When the switching frequency of the converters is close to the millimeter level, the switching loss of the conventional silicon MOSFET increases sharply, resulting a decrease in the overall efficiency of this converter. The cascode gallium nitride transistors are more suitable for critical current modes (CRM) boost PFC converters, analyzing and comparing the static characteristics of the cascode gallium nitride transistors and silicon devices could help us to analyze the conducting losses of both. The pre-simple analysis of gallium nitride devices and CRM boost PFC converters is the basis of applying gallium nitride devices to high-frequency CRM boost PFC converters. Therefore, the static characteristics of the cascode gallium nitride transistors and silicon devices are analyzed and compared in this paper. The power factor correction principles with switching modes and steady states for the CRM boost PFC converters are discussed. The output characteristic curves of silicon MOSFET IRF 8707, depletion gallium nitride HEMT TPH 3206PD, and cascode gallium nitride transistor TPH 3206PD can be seen in figure 1 to 3. It can be seen that the output characteristics of the cascode gallium nitride transistor are similar to that of power silicon MOSFET in the first quadrant. Still, it does not show that characteristics in the case of reverse conduction in the third quadrant. It's mainly because the cascode gallium nitride transistor has a cascode structure. Its reverse conduction voltage is the sum of reverse conduction voltage of power silicon MOSFET and depletion gallium nitride HEMT. Therefore, the reverse conduction voltage of the cascode gallium nitride transistor is slightly higher than that of silicon MOSFET of the same voltage level. According to the difference of static characteristics between the cascode gallium nitride transistor and silicon devices, the superjunction silicon MOSFET of Infineon, CoolMOS IPP65R125C7, as representatives of current high-performance silicon devices are selected. The rated voltage and current are similar to TPH 3206PD, which is suitable for the comparative analysis. Some parameters of TPH 3206PD and IPP 65R125C7 are shown in Table 2. And now we will talk about the basic principles of CRM boost PFC converter. The basic principle of a single-phase CRM boost PFC converter consists of two parts. The first part is the working mode of main switches S in a switching cycle, and the second part is the principle of power factor correction. The central circuit topology of the single-phase boost PFC converter is shown in Figure 5. Figure 6 shows the equivalent circuit of the converter when the switch is on and off. Figure 7 shows the changes in switch voltage, inductance current, and voltage. After the theoretical analysis, an experimental platform was built and the test data was analyzed. Figure 9 is the structure diagram of the dual-pulse test platform, which including driving circuits and DC power supply VDC, filter capacitor CT, inductance LT, freewheeling diode DT, and switch ST to be tested. Other parameters of the dual pulse test platform are shown in Table 3. In the dual pulse test of the cascode gallium nitride transistor, the current before turning on is 0 and the conduction current is 3.84 amperes, 2.04 amperes, 1.48 amperes, and 1.23 amperes respectively. 4 groups of switching waveforms are obtained by changing the switching current, by changing the time of the first pulse, and as shown in figure 10 to 13. The converter reaches steady states quickly. In order to test whether the CRM boost PFC converter based on GaN devices can achieve the goals of high power factor and more than 90% efficiency in the entire input range, the root mean square value of voltage at 85, 160, 220, 265 are selected for the experiment, and the results are shown in figure 14. When the CRM boost PFC converter reaches the steady state, the output voltage waveform is shown in figure 15. The measured output voltage ripple is about 12.6, less than 55%, which conform to the theoretical and simulation analysis. The dual pulse test platform based on the cascode gallium nitride transistor TPH3206PD is built, and the experimental platform of a 200 watts single-phase CRM boost PFC converter is described. The stability of the high-frequency driving circuit of gallium nitride device is verified by the dual pulse test platform, which effectively avoids false turn-off phenomenon in the turn-on process. The switching loss of TPH3206PD is measured experimentally, and the accuracy of theoretical calculation is verified. The experimental results show that when the operation frequency of CRM boost PFC converter is close to 1 MHz, gallium nitride devices can effectively reduce the switching loss and improve the overall efficiency. Thank you very much for watching my presentation, and don't be hesitate to contact with me by email. Thank you very much. Goodbye.